let's stay with the idea of sequence-to-sequence model for a second. So here you see a representation where I'm not interested too much in the decoder, so you see that the decoder is just a green box. Let's focus on the encoder. So we said that the encoder is just running over the input sequence. We are not interested in the output, but we are interested in the fact that all the relevant information from the input sequence should be in this element that here is H2, so in the last internal state of the encoder, because that's the only element that goes to the decoder. And one thing to notice is that this hidden state, H0, H1, H2, H2 in particular, it's a vector, and it has a fixed size. It's not something that I can change while training. So in this particular example, there is no problem. The sentence is je pense que. It's very short, there are very few information, and we are, and most probably, the encoder will be able to store this information in this vector H2. So it will work. But we may have example where the input sequence is very long. And in this case, the problem is that now I have a lot of information that the decoder is trying to extract and is trying to store in the last internal state, in this case Hn. The problem is that Hn has, again, fixed size, so has the same size as in the previous example. And now you can see that it's easy to find a sequence that is long enough so that the information will not fit into this internal state Hn. And that means that we will lose some information, and that means that the decoder will not be able to produce the correct output. And again, the key intuition here is that there is just one point of communication between the encoder and the decoder. And on top of that, this point of communication has a fixed size. So that's the problem that we have here, which is this bottleneck that I mentioned in the slide that we would like to solve. So yes, so here is what I said before, that if I don't have any constraint on the length of my sequence, I can always find a sequence where I have so many information that it will not fit into a fixed size vector. Let's see how we can solve this problem. So one possible solution is actually if I can find a way for my decoder to look back to the input sequence and try to extract the relevant information when it's trying to produce the output. So the idea here is that the encoder will still do its work and will still give this Hn internal state to the decoder, but the decoder, while producing the output at every time step, he has some special way of looking back at the encoded sequence here, this H, and extract the information that he needs. So that's what we would like. We still don't know how to do that, but you can see that if we can find a way to do that, now the information can flow much more easily, because at every time step, the decoder can just look back and extract the information that it needs. And here the key word is this selectively look back, because we want the decoder not only just to go back to the encoded sequence and get all the information, we want the decoder to just focus on the information that are relevant for the current state of the decoder, for the current time step. And actually this is the key, this is the idea of attention. So attention is basically some mechanism that we will see how to implement later that is helping the decoder to decide which information are important from the input sequence for the current time step. And to make it more clear and give an example, if the decoder is in the state when he's trying to produce the word thing, so the translation for the word pons, we would like this attention mechanism to look back at the input and extract the information from the word pons. So to understand which word is important in this sequence for the current state, where the current state in this case is to produce the word thing. And to formalize it a little bit more, so the attention will be a function. So it will be a system that will help the decoder to find this relevant information. And we said that the decoder, this function will work with two inputs. The first input is this sequence. So this is sequence H, where the attention should try to find the relevant information. And the other information that the attention the attention function has, the other parameter, is this the decoder state S. So what the decoder is trying to do. Like if you remember the example before, the decoder was trying to produce the word think. So that was our state, and we had the sequence with all these words, and we said that the attention function should be able to tell the decoder the information that you want come from the element number 1 in this sequence, which is the word punks. So we still don't know how to implement this function, but this is what we would like to have from this function. And to do one step more, when we say that the attention is trying to find which element is important in a sequence, it basically means that the attention is assigning some weights to all the elements in this sequence, and these weights are telling the decoder which information is important. And these weights are obviously normalized, so all these weights are from 0 to 1, and if we sum all the weights over this sequence, we end up with a sum of 1. So this is basically what the attention is trying to do. And what happens after we have these weights, which we assume are correct, like in this case, again, with the example we were producing the word think, you can see that the biggest weight is on the word punks. You see that the weight W1 is 0.6. So what we do at this point, we just do a weighted sum, so something like this. So basically, you see that we are doing this sum that is scaled on the importance of the element. And at the end of this weighted sum, we end up with a vector, which we call C, which is also called the context vector, because this vector represents the information that are relevant for the decoder to produce the current output. And in fact, at this point, we just feedback this vector into the decoder, and now the decoder can hopefully do a better job in producing the output, because it has all the relevant information that it needs for the current time step. To make it more clear, well, first let me say that we still didn't show how to implement this attention A, which we will do later. For now, you can think that of a black box that is doing the right thing. But before going there, let's show a step-by-step example which will show how the attention works. And you will see that this example is basically very similar to the sequence-to-sequence example that we saw before, except that now we will add this additional component of attention. And in fact, you can remember this example. So we use the Je suis malade. So we were trying to translate French to English. And we said that we saw in the previous sequence-to-sequence system, so the one without attention, that we were running the encoder. And now we are doing the same thing. So here, nothing changed. At this point, we still don't have attention, because attention is something that happens in the decoder. So here we do exactly the same thing. We run the encoder over this sequence Je suis malade. Again, the encoder, we are not interested in the output. We are just interested in how it is encoding this information in the various H. And in particular, the last H will be what we will send to the decoder. Even if then the decoder will also be able to use attention. We will see how. But for now, let's say the encoder is doing this, is producing this internal state, and in particular, the internal state H2 will be given to the decoder. And you see that we have exactly the same problem as before, like H2 has a fixed size. So up to here, nothing changed. And then we initialize the decoder, and again, nothing changed here. You see that we are sending this H2 to the decoder. So the decoder is initialized with this last internal state that was coming from the encoder. You see that we have this start of sequence symbol here, which again is a signal for the decoder to start to run, to generate the text. And we'll use the decoder in an autoregressive way. So up to here, everything is exactly equivalent to before. But before updating the internal state, so before doing the decoder job, this is where we use attention. So attention which again now is just a black box, attention is, we mentioned that it has two inputs. The first input is the decoder state, and the second input is this sequence from the encoder. So let me show this on the slide. So you see that attention is getting the decoder state, which actually, given that we are at the very first step, is the last state from the encoder. But attention is also looking at the various elements here, so H0, H1, H2. And we didn't specify how, but somehow attention will come up with some weights, then we will do a weighted sum, and we will end up with a context vector. So I show it here in red, so this is the context vector, but you can also see here on these attention lines that one is more thick. And this is because hopefully attention here is doing the right thing and is giving a big weight to the first word, je, just because it understood that the decoder now needs the information coming from this word to produce the current output. And in fact, now we can finally run the decoder. So the decoder now has input the start of sequence, the previous internal state, but also the attention context vector, which hopefully is helping the decoder to update the internal state. So we have now S0, and to produce the output, which is in this case the word I. And given this is autoregressive, this will become the next input. Now we are on time step 1, so the second one for the decoder. And you see that now we apply attention again. So this is a key point. So before the decoder will update the internal state, we will run attention again. So this part here, you can see that attention took as input the previous internal state from the decoder, and again is looking at the encoded sequence here from the encoder. And now the attention is the highest weight is on the second word, because because the decoder is trying to predict this, the verb of this sentence. And this information goes into the decoder, so the decoder can create this internal state S1, and then we can produce the output M. And you can see that M becomes the next input, because again we are in an autoregressive case. And again, here, before updating the internal state S2, we will run the attention again. So you see how attention is run at every time step. And this gives the decoder a lot of flexibility, because now at every time step, it can go back and extract the relevant information. And it definitely improves the flow of information in this model. So in this particular case, okay, the decoder is initialized with the attention takes as input the previous internal state, S1, is looking at the encoded sequence here, and is deciding that the most important word is this malad, which is the third word, so is putting a high weight here. And then we are doing a weighted sum, and we have this context vector here that goes into the decoder. So now the decoder is hopefully is updating the internal state S2 in the right way, and is producing the output SIG, which is the correct one. And then we have still one step to run, because the decoder will continue to run until it decides that it's time to stop by producing the end of sentence string. And again, you see that before updating this S3, we ran the attention mechanism again. So you see that it runs at every time step. So at this point, it should be clear why the attention works much better than without attention. If we have a lot of information coming from the encoder, without attention, we have a bottleneck here, and eventually we will fill this internal state H2. But now, the internal state H2, it is used to initialize the decoder, yes, but the decoder has this flexibility that at every time step, it can go back and extract the information that are relevant for that time step, and then produce the output. And it can do that, again, iteratively at every time step, so it's much more information than the system that we presented, so the sequence to sequence without attention.